All right, here we go. Final final four. We're going to continue to build upon the vocabulary that we've been talking about with the midline, the amplitude, and this idea of translating trigonometric functions horizontally. Don't be flustered if it's pretty frustrating. It's always a challenging topic. Further compounded by the fact that we're talking about trigonometry at the same time. But we're going to look at how we can change the value k, right, the scale factor of the input, and how that actually modifies the graphical representation. And then we'll know we've got it when we can identify the midline, amplitude, and horizontal translation of a trigonometric function given a graph or an equation. So in this case, we have two different musical notes, or the sound waves for those two musical notes. What do you notice? What do you wonder? And a fun fact is the amplitude of a sound wave relates to how loud the sound is. So the larger the amplitude, the louder the sound. So remember, if you've forgotten, the amplitude is the distance between either the maximum or the minimum value and the midline, right? So the more stretch we have, the louder you're listening to your music. And the period of sound wave is related to its pitch. So more highs and lows in the wave indicates a shorter period, which indicates a higher pitch because that frequency is happening rapidly, right? I know it's something we spoke about in the last lesson at great length too, but here are some functions. As you can see, some have their inputs modified, as we have in situations like this. Some have just a scale factor applied to the function itself, and some have their outputs and scale factors applied simultaneously. So look to match up which graphs go where. But notice that more than one equation can match the same graph because these functions are periodic. So it is quite common that we can represent the same type of behavior using two different functions. All right, but let's have a conversation about this. Okay, so normally our sine function, right? We're told that this is the sine function. Normally our sine function starts out at a value of 0, but I can clearly see that it's about, I want to say maybe 7. Or 7.5. The difference. However, okay, that tells me the midline of my graph, right? This value of 7.5. But if I try to draw a straight line, and I think I'll be able to do that actually. Yep, here we go. The midline is supposed to create symmetry between the maximum and minimum values. So that's something that we're going to need to adjust for. If I draw a line here at about 15, I can see that it looks much more symmetrical. All right. Now, as far as the amplitude, right, I have a height of maximum of 25 and a minimum of 5. So the distance between those two is going to be value of 10. And I'm going to apply that as my scale factor. Okay. Last and most certainly not least are the adjustments that we might need to make to this function and its input. Now, the input, we should look to first see what happens when we substitute in a particular value. So if I substitute in 0 into the sine function, sine of 0 is 0. 0 times 10 is 10. But when I add 15, I get a value of 15. So the output when theta is 0 currently is 15. And as we can see, graphically speaking, that is not the case here whatsoever. So what I need to do is I need to determine whether or not I need to push the function to the right or to the left. Unfortunately, I should have given you some sketch tools here. But remember, if we add an angle of rotation, it is going to move the graph, or we are moving counterclockwise. but we are moving the graph to the right. And if I subtract, I am pushing the graph to the left. So in this case, notice how we have our maximum value at an input of 3 pi over 4. In order for that to occur, we need to think about where does the maximum value for sine typically occur? And that maximum value for sine is at the value of pi over 2. At pi over 2, the value of sine is 1. That's its maximum value. So how can I modify 3 pi over 4 to make it emulate pi over 2? Well, I can subtract pi over 4, and this simplifies that situation. Now, I'm going to turn it to you and ask you to do the same thing, but for the cosine function. Here, you'll see what is happening to at least the algebraic outputs for this function, sine of 2 theta, with this table. This will be a great way to check whether or not you have certainly mastered the unit circle. You'll take those values from your previous screen in this table and plot them accordingly. The graph that you see here, you should recognize as the graph of sine. So you'll be able to sketch your graph and compare it to the graph of sine theta. Make a prediction as to what the graph of cosine of 4 theta will look like and make a sketch. If you want, you could even include a graph of cosine as well. And that's where we're going to pause.